Welcome to Lecture 25, 6.1, Discrete Random Variables. So, definition. A discrete random variable is a numerical measure of the outcome of a probability experiment, so its value is determined by chance. Random variables are typically denoted using capital letters, such as capital X. So this is where distinguishing between using a capital and a lowercase letter is going to become more and more important as we go along. So always keep that in mind. Switching between a capital and a lowercase is not a good idea, in math especially. Alright, some more definitions. There are two types of random variables. So there's a discrete random variable, oops, I already wrote variable. So a discrete random variable, which either has a finite or a countable number of values. And the values of a discrete random variable can be plotted on a number line with space between each point. For example, if we have a number line, I can plot the points 0, 1, 2, 3, and 4. So the graph would look something like 0, 1, 2, 3, and 4. So we typically would use the counting numbers. And then the other variable we have is a continuous random variable. Which has infinitely many values. The value of a continuous random variable can be plotted on a number line in an uninterrupted fashion. So, what a plot would look like, we would have 0, 1, 2, 3, 4, oops. But instead of distinct points for all of them, it would just be continuous. So just cover all of those points. So that would be the main difference, or the difference. For example 1, identify the following scenarios as discrete or continuous random variables. Alright, so A. Let the random variable x represent the number of B's earned in a section of statistics with 12 students enrolled. What kind of variable is x, and what are the possible values of x? Well, let's see, the possible numbers of B's. Well, x would be, for example, there might be 0 B's in the class. There could be 1 B, 2 B. But could there be infinitely many number of B's in the class? No, there's only the counting number of B's, right? And the only possible counting numbers are from 0 to 12 B's in total. Okay, so this is looking like a discrete random variable. Alright, so this is a discrete random variable. And then for B, let the random variable y represent the temperature. Ooh, had a double there. Hopefully I fixed that on your notes. The temperature during the daytime in Kailua. What kind of variable is y, and what are the possible values of y? Okay, so what are the possible values of y? Could I list them out? You know, I really couldn't measure it out. It's continuous. The temperature doesn't really have sort of that counting point that we would have for the grades. So this would actually be, in Hawaii, we'd probably say y would be greater than 55, I would say. This is very, very general. But for example, we wouldn't say that there are specific values for y like here. Because sometimes the temperature is in between. Maybe it's 87.95, maybe it's 87.96, and so on. So y is not a discrete random variable, it's actually a continuous random variable. And C, let the random variable s represent the number of people purchasing a coffee from Starbucks in the morning. What kind of variable is s, and what are the possible values of s? Well, let's see. Thinking about the number of people, you only have sort of the counting number for the number of people, right? You could have 0 people, you could have 1 person, 2, 3, and so on. So even though, in a sense, it could go on to forever number of people, at the same time you still have that spacing in between each of the numbers when you're counting. So this is going to be a discrete random variable. So we'll say S represents a discrete random variable. For number 2, identify discrete probability distribution. All right, the probability distribution of a discrete random variable x provides the possible values of the random variable and their corresponding probabilities. A probability distribution can be in the form of table, graph, or mathematical formula. For example 2, suppose we ask a basketball player to shoot 3 free throws. Let the random variable x represent the number of shots made. Alright, so what are the number of shots possible? Well, he could make 0 shots, 1 shots, 2 shots, or 3. Because at most we have 3 throws. Alright, so the table provided shows a probability distribution for x. So for the number of throws, for example, the probability of shooting 0 is 0.01, the probability of shooting 2 throws is 0.37, probability of shooting 3 throws and getting it in is 0.52. So, with this notation, what does this mean? Well, this is saying what is the probability of 3. So the probability of 3 is going to equal 0.52. The next one, what is p of 0, or the probability of 0? Well, the probability of 0 is going to equal 0.01. Now let's see, rules for a discrete probability distribution. All right, let p of x denote the probability that the random variable x equals x. Then we have the following. The sum of all the probabilities should equal 1. This is something we have seen before. And all of the probabilities should be less than 1, less than or equal to 1, and less than or equal to 0, which is also something we have seen. So they should not be bigger than 1, and they should not be less than 0. So we're going to identify which of the following are discrete probability distributions. So what we want to use are these 2 rules to see which one satisfies all of them. So first off, let's take a look at all of these numbers. We're going to add them up and see if they equal 1. So this is for rule 1. We have 0.19 plus 0.26 plus 0.24 plus 0.31. What does this equal? This equals 1. Okay, so that works. That checks out. Now rule 2. Actually, so we can write this out. We can say the sum of the probability of x equals 1. And rule 2. We need to make sure each one is less than 1 or greater than 0. And looking at all of them, they are all less than 1 or greater than 0. So for all p of x, we have 0 less than or equal to p of x, which is less than or equal to 1. Okay, so what does this mean? Well, this is a discrete probability distribution. Squeezing it in here. Distribution. Period. Alright, now let's take a look at the other one. So rule 1. What are we checking? Well, we want to make sure that when we add them all up, it equals 1. Not more than and not less than 1. So 0.20 plus 0.15 plus 0.27 plus 0.41. What does this equal? Oh, this equals 1.03. So the sum of p of x is not equal to 1. So it breaks one of the rules, which means this is not a discrete probability distribution. Now let's take a look at the next one, Rule 1. Rule 1, we're going to go ahead and add these all up, see if it equals 1. So 0.25 plus, a negative 0.25 plus 0.40 plus 0.10. The work is not looking that great. So we come out with the answer of 0.5. So the sum of p of x is not equal to 1. So it breaks one of the rules, which means it is not a discrete probability distribution. And another thing to note about this one, which was suspicious, is we had a negative. And recall, for the last rule, it has to be greater than 0. So that would not have worked either. Now let's take a look at objective 3, graph discrete probability distributions. So in the graph of a discrete probability distribution, the horizontal axis represents the values of the discrete random variable, and the vertical axis represents the corresponding probability of the discrete random variable. So x and then p of x. Now, for example 4, we're going to graph the discrete probability distribution from the given table. So here we have our given table, which we worked with before. And let's see, for graphing this. Well, what are the values that we have? We go from 0.01 all the way up to 0.52. So how should I'll go ahead and just do this in 0.1. That'll be the first one. 0.2, 0.3, 0.4, 0.5, and 0.6. Okay, so these are my x values, and these are going to be p of x on this side. Let me move this over so I can write that in. Okay, awesome. Now, let's go ahead and graph these. So the first one, we have, actually, let me label the bottom, actually. We go from 0 to 3. So this is 0, and then we'll do 1, 2, 3. Now let's graph these. Well, 0, 0.01, so that's just right about there. As usual, always mark our dots. If there start to be more than like 9 points, usually I would not require you to label all of them. But if there's less than 5, you should be labeling them. And if you're not certain, you can always send me an email during an exam. And if I don't get back to you, usually I'll give you the points back for that because you did ask me and I was unable to get back to you. But normally I'm waiting around during the exams to answer questions. Okay, so next is 0, 0.1. Right there. And then we have 2, 0.37, so almost at 40. We'll go ahead and fill this in here. And 2, so almost at 40. Right there. So notice we draw that line for the graph. And lastly 3, 0.52, so a little higher than 0.5. Ooh, that should not have been a 0 on all of those, sorry. That was incorrect. That should be a 1, 0.1, 2, 0.37, and 3, 0.52. Alright, there we go. We've just graphed the discrete probability distribution. Now we're going to compute and interpret the mean of a discrete random variable. Alright, so for example 5, a kid went around his neighborhood to determine the number of pets that his neighbors owned. He found the following data: 2, 4, 6, 6, 4, 2, 3, 4, 5, and 5. What is the mean number of pets that his neighbors own? So we could take the normal approach and add up all these values and divide by 10, but we're going to try to take a different approach, which will help us further down the line. So first we're going to fill out a table. Oops, let me change the color. So what are the possible dogs we have? We have pets. We have 2, 3, 4, 5, and 6. Those are the ones we have. And there are 10 total observations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. So how many 2's do we see out of the 10? Well, we have 1, 2. So that'll be 2 out of 10, which is going to be 0.2. And then for 3, how many 3's do we see? Just 1. So that'll be 1 out of 10, which is going to be 0.1. And then how many 4's do we see? 1, 2, 3 4's. So that'll be 3 4's out of the 10, which is 0.3. Now, how many 5's do we see? 2. So 2 out of the 10 were 5's, which is 0.2%, or 20%. And then how many 6's do we see? Also 2 6's. Now, what are we going to do with this data? So we're going to start this off by solving for the mean, the normal way we do, and then I'll explain why we found these values. Alright, so normally for the mean, you find the sum of all the values that you have and you divide by the total, right? So in our case, it would be 2 plus 4 plus 6 plus 6 plus 4, I'm getting them from up here, plus 2 plus 3 plus 4 plus 5 plus 5, and dividing by the total number that we had, which was 10. Now I'm going to rewrite this so that all of the same values are together, so that the 2's are together and the 3's and so on. So we had a 2 plus a 2, and then a 3. So I took those ones. And then we took the 4 and the 4, and the other 4, so there are 3 4's. Then we had 2 5's, and lastly, 2 6's. So let's see, how many did we have again of each? So we had 2 of those, 1 of these, 3 of these, 2 of these, and then 2 of the 6's. Now another way to represent these is to use multiplication instead of the addition. So 2 2's is just seeing 2 times, right? And then 1 3 is just seeing 1 3 is just seeing 3 one time. 4 3's is seeing 4 3 times. 2 5's is seeing 5 2 times. And 2 6's is seeing 6 2 times. So I've replaced the addition with some multiplication and divide by 10. Now I'm going to go ahead and kind of use a reverse addition. So normally, let's see on the side here real quick. If you have two fractions that you're adding together, for example, 1/3 plus 2/3, what do? Well, you keep the denominator and you add the exponents, 1 plus 2, right? So what we're going to do is the exact opposite. We're going to take all of the additions and split them up into their own fractions. So I'm going to split them up at their addition points. Okay, so just kind of reverse addition. Now what is that going to look like? So this would be 2 times 2 over 10 plus 3 times 1 over 10 plus 4 times 3 over 10 plus 5 times 2 over 10 plus 6 times 2 over 10. Now notice these are actually all supposed to be over 10, but I can rewrite this as 2 times 2 over 10 plus 3 times 1 over 10 plus 4 times 3 over 10 plus 5 times 2 over 10, and lastly plus 6 times 2 over 10. So if you'll notice, what we managed to sort of maneuver into this problem was each of the numbers being multiplied by their probabilities. So notice, the 2 was being multiplied by its probability. The 3 got multiplied by its probability, the 1/10. The 4 got multiplied by its probability, the 0.3, and so on. So we can rewrite it that way. Another way to rewrite it would be 2 times the probability of 2, plus 3 times the probability of 3, oops, too many parentheses, and so on for each of the values. which will be, let's go ahead and type in those probabilities. And then we can plug these into a calculator and we get 4.1. So my mean is 4.1. So our answer would be the mean number of pets is 4.1. Okay, so that was just sort of a fancy way of showing how you are able to manipulate the original formula for the mean into the formula that we are going to be using now. So the mean of a discrete random variable is the following. The mean of x is going to be given as the sum of your x value times the probability of x, which is what we did right here. It was the sum of each of the values times their probability. For example 5, compute the mean of the discrete random variable in the given table. Alright, so now we're going to use the new formula. So the mean of x is going to equal the sum of the random variable times the probability of that random variable. So we're given random variables and their probabilities. Go ahead, pause the video, and try to see if you can find the mean by yourself. Alright, so first off, we have 0 times its probability, which is 0.01, plus the next one is 1 times its probability, which is 0.10. Plus, and the next one is 2 times the probability of 0.37, and lastly 3 times the probability of 0.52. Then we get the following values, so that becomes 0 plus 0.10 plus 0.74, and lastly plus 3 times 0.52, which is 1.56. Okay, we can add all of those up. So 1.56 plus 0.74 plus 0.1, 2.4. So the mean of x is 2.4. Okay. So here's a question. How do we interpret the mean of a discrete random variable? Well, as our book says, the mean of a discrete random variable can be thought of as the mean outcome of the probability experiment if we repeated the experiment many times. So if we repeated the experiment, which we had an example above with the person shooting 3 throw baskets, then we would expect the mean number of free throws to be around 2.4. So another way of saying it is, if the experiment was repeated many times, we would expect the mean to be around 2.4 for our problem. So now, interpretation of the mean of a discrete random variable. Suppose an experiment is repeated n independent times and the value of the random variable x is recorded. As the number of repetitions of the experiment increases, the mean value of the n trials will approach u of x, the mean of the random variable x. In other words, let x sub 1 be the value of the random variable x after the first experiment, x sub 2 be the value of the random variable after the second experiment, and so on. Then we would have x bar equals, so the sample mean, all over our values added together until we get to the last one, divided by n. So what should happen is the difference between our sample x and the theoretical mean will get closer and closer to 0 as n increases. So basically it's saying the more and more times you conduct the experiment, the closer your x bar, or sample mean, is going to get to the theoretical mean. Now let's take a look at example 6. The basketball player from example 2, which we went over, is asked to shoot the 3 throw 25 times. The given table shows the result of the experiment. Compute the mean number of free throws, then compare this result to the theoretical mean found in example 5. Okay, so what we're going to do here is, because we repeated the experiment a ton of times, hopefully the mean we find will be closer to 2.4, which we found previously in example 5. So let's go ahead and compute the mean here. To do that, first I'm going to go ahead and add up these values here, because I know x bar is going to equal all of those values added up. I'm not going to write them all out, but I know it's going to be the sum of xi divided by n. Now, what is n? N is 25, because that's how many items we had. Now let's go ahead and find the sum. So adding up these values, I have 5 and 5, so 11. And then 9, 10, 11 again. Here I have 5, 6, 7, 8. And then 5 and 3, so 8. And then we have 2 5s, so 10. All right, now we're going to go ahead and add all of these up. And we get 22 plus 10, so 32, plus 8 plus 8, so 32 plus 16, we get 48. So the sum is going to be 48, and 48 divided by 25 is about 1.92. So at the moment, this is really not that close to the mean we had originally. Remember, the mean we had originally in example 5 was 2.4. But this is close. So what would we do? We would expect, so if we did the experiment more times, like maybe 100 times, we would expect x bar to be closer to 2.4, which is the theoretical mean. So in this case, the actual mean we found from the number of times we did the experiment, which is only 25 times, was not as close to the theoretical mean. But if we did this experiment many, many, many times, it would start to get closer and closer to the theoretical mean. Let's take a look at objective 5. Because the mean of a random variable represents what we would expect to happen in the long run, it is also called the expected value. All right, example 7. A term life insurance policy will pay the beneficiary a certain sum of money upon the death of the policy holder. So basically, for example, if someone decided to get an insurance policy, this is the policy holder. This is saying if he dies, the money of his policy will go to the person who is his beneficiary. So oftentimes, especially back in the older days, what I can think of, is the man would get an insurance policy because back then the women didn't always work, so that if he died, she would have money to live off of. Nowadays, people do it, parents do it for their children, and so on and so forth. So that's a basic concept if you're not certain on that. The very basic concept. All right, so these policies have premiums that must be paid annually. Suppose an 18-year-old male buys a $175,000 one-year term life insurance policy for $195. According to the National Vital Statistics Report, the probability that a male will survive the year is 0.998937. Compute the expected value of his policy to the insurance company. Okay, so once again, these policies are talking about if the person lives or dies. So, our experiment has two possible outcomes, surviving or dying. So we're going to let X represent the payout. Money lost or gained. Which depends on the survival or the death of the person who has the insurance. So what is the probability that the person survives? Well, we know that right there. It's 0.998937. And then the question is, what is the probability that the person does not survive or dies? Well, that probability is just going to be 1 minus this probability, which we would get out to 0.001063. All right, so what does the payout mean? Well, basically what this means is that if the 18-year-old survives the year, he pays the company $195. If he doesn't survive the year, the company has to pay his beneficiary this much money. Which is often why a lot of times, if you ever look at insurance policies, they have a rule about dying within a certain amount of time. Because I think back before they made those rules, sometimes if this person here was desperate for money to take care of their family member, they would kill themselves to give the family member their money, which a lot of insurance companies didn't want. Why? Because they only paid this much money, and the insurance company has to pay their beneficiary a ton of money. So there are a lot of sort of safe holds that insurance companies are doing now. That was just a random side lesson. I believe that's one of the main themes in that movie, It's a Wonderful Life, which is a slightly sad movie, but I do recall that happening in the movie. Okay, so now what are we looking at? Well, if the client survives, the insurance company gets the money that they would pay, right? So, $195. Sex would be $195. Now, if the person dies, what does the insurance company have? Well, if they die, the insurance company still gets the $195 that person paid them, but they have to end up paying their beneficiary a ton of money, which they really don't want to do. But because he's young and healthy, that probability is supposedly lower of him dying. And so this is going to come out to be about, I'll go ahead and round it to the nearest dollar, which will be negative 174,998. The insurance company does not really want to pay that out to people. They want you to keep living so they can keep making money. Okay, so then what is the expected value of the policy? And this is, remember, from the point of view from the insurance company. We would have the expected value of x is going to equal, well, the mean of x, which is the sum of the x values times their probabilities. And that is going to come out to, so we have the probabilities and the x values. This should have been x of 1, x of 2. So we have 1.95 times the probability of survives, plus the negative 174,998 times the probability that they die. Let's write this out. So that's 195 times the probability of survival, which is 0.998937, plus negative 7,4998 times the probability of dying, which was 0.001063. And so this value here is going to be negative 186. I'm going to keep to the nearest zeros there. And let's calculate the other one. All right, rounding this one out to the nearest dollar, that'll be about 195. Oh, okay, minus the 186. I'll rewrite that and erase the other one. And what do we have? We get about 9. So what does this mean? Well, this is saying that the company expects, I'll write this down, the company expects to make $9 off each 18-year-old male client it insures. So this is not saying that this is a long-term result, but what it's saying is that it expects to make an average profit of $9. But as you noticed before with the other example in the basketball, in order to get your mean close to that value, you need to have lots of these experiments. So this works better for more and more of the number of people that you insure. All right, now objective 6, compute the standard deviation of a discrete random variable. So the standard deviation of a discrete random variable x is given by the following. Sigma of x is equal to the square root of the sum of x minus the mean squared times the probability of x. This is the first version, or the second version of the equation is the square root of the sum of x squared times the probability of x minus mean of x squared, where x is the value of the random variable and mu sub x is the mean of the random variable and p of x is the probability of observing a value of the random variable. For example 8, find the standard deviation of the discrete random variable given in the provided table using both formulas. So actually, due to the amount of space that I have here, we're just going to use the first formula. But if you'd like to, you could go ahead and try using the second formula by yourself and see if you can compare the answers and see if they come out the same. Alright, so to set this up, what we want to do, first I'm going to write down the formula we're using to get a better idea of what I need to fill it out. So what I need to fill this out is I need the mean, which we're going to use given the following. So I'm going to give the mean of 2.39. I'm going to type this into the actual notes and re-upload them. And then we want to find the subtraction between our x values and the mean, square that, and multiply it by the probability, which we have right there. So let's set up a chart for this. We have x values, 0, 1, 2, 3. Then we have our probabilities, which we already are given, 0.1 or 0.01, 0.10, 0.37, and 0.52. Next, to fill this out, we want to take the subtraction of the values, then square it, and lastly we'll take that and multiply it by the p of x value. Okay, so to set up this first part, we're going to do the x value minus our mean, which I'm given right there, so 2.39, and then square it. So I'll set that up for all of them. Okay, I'm going to go ahead and pause the video and fill this out. Alright, so we get those values. Now we'll take those and multiply them by the probabilities. So let me first copy them down, and we'll multiply them by the probability. So for p of x, for the first one we have 0.01, second one 0.10, third 0.37, and lastly 0.52. Okay, I'll pause the video and fill these out. Okay, and we get the following values. So lastly, or not lastly, almost lastly, we want the sum of these. So the sum of my x minus my mean value squared times the p of x. To find that, we'll add all of these up, and adding those up, what do we get? We get 0.5001. So lastly, for this formula, what we do, we take sigma of x, and we're going to square root this value. Well, that value, 0.5001, let's go ahead and take the square root of that. So my calculator gives me about 0.7. There we go. The standard deviation is about 0.7. Alright, so that is it for this lecture. You can see example 9 on page 304 for help on using any of the technologies for computing the mean and standard deviation for your homework. But as usual, remember for the exams, doing it by hand is what I'm looking for. Please email me if you have any questions.